responsible for localization and for building new services based on ones we have in our headquarter, and also for project management of different digitalization project in the industry for mainly for manufacturing. So first of all, I would like to give an overview of the technology itself, of IoT technology. Let's start from the definition. The Internet of Things is a global infrastructure that allows physical and virtual assets to communicate with each other. It's the general definition, and important thing that it's infrastructure, and that we are talking not only about physical assets but also about virtual assets. For example, it can be some IT systems or OT, operation technology systems at the enterprise. And for what we want these physical and virtual assets to communicate with each other. Mainly to solve new tasks and to solve old tasks more efficiently through interaction and joint activities. So I want to separate two aspects here. First aspect is that the ability to communicate makes things smarter. Take a simple example of a refrigerator. If we have a simple just refrigerator, it can support needed temperature. But if we add some smart module to this refrigerator, it can then, for example, monitor the outside temperature, and it can modify some modes of this refrigerator, or it can enable such so-called anti-frost system. But if we then add connectivity ability, so that this refrigerator is connected to the internet, there is a really wide opportunity for this refrigerator. For example, we can add a special screen, and we can add special apps to this screen so that we can add some notes so that we can listen to music via Spotify or something like that. We can connect this refrigerator to a smart home system, or we can for example, even make this refrigerator buy products by itself, so that this necessary products that refrigerator see that they are needed, the lack of such products, so that it can buy it, and some delivery company just provide us with that stuff. So the thing that the ability makes things smarter, and even the communication, sometimes it's even more effective to make them think whatever it is they think, to make it smarter than to provide it with some embedded resources to calculate something. So connectivity is sometimes even more effective. And this brings us to the second aspect, that joint activities allow us solving new tasks. For example, if we're talking about people, it's quite obvious and it's quite clear that a group of people can solve more tasks and more complex tasks than if they are just single separate persons. For example, catching a mammoth, so it is a task that's only possible for a group of people, or every project we have today presupposes that we need a group of coordinated people. And the similar thing we have when we're talking about things. So the joint coordinated activity of things makes it possible to solve new problems and implement new joint scenarios. For example, I saw a news that's, for example, in Hawaii, uh, the price for tickets on airplanes is changed based on data from sensors that are located in the waves. So if we measure somehow waves via video cameras, for example, and then we have a special algorithm that changes these prices on airplanes, we have a new scenario that can be more effective for both for every party of this. So now we have so-called Internet of People and the Internet of Things combining into a single integrated network. So we have really a lot of people connected to the internet, and also now a lot of things connected to the internet. So we have such integrated network, and all the parties are closely connected to each other. And just to add some numbers here, there are already 3 times more connected devices than people on Earth by now, and we expect this number to grow. For example, by the end of 2025, we expect almost 80 billions of connected devices. Consequently, IoT market and the market of IoT platforms are growing really fast. It's more than 20% per year. And the distribution of revenues in this value chain is also changing. We see that the hardware that hardware share here is really decreasing, and the role of platform software and applications are really increasing very fast. So we expect by 2023 a market of almost $200 billion here. And just to classify how IoT is classified, we have non-industrial, partly industrial, and industrial IoT. If we are talking about non-industrial, it's generally consumer goods, it's electronics. Partly industrial, it's e-commerce, healthcare, and really interesting part of the IoT is industrial IoT. It's all that's related to building automation, agricultural and gas, transport, automotive energy, and manufacturing. And now I would like to show the role of industrial IoT in enterprise digital transformation. You all, I think, know and understand that, and see it in your life, that we have really digitalizations in many industries now. So you all use smartphones, you all probably buy a delivery of food, or you all listen to music that has some AI algorithms, artificial intelligence algorithms to personalize the music you're listening to. And the same thing is happening now in manufacturing. So it's really a tipping point now for manufacturing. And this is connected to Industry 4.0. Industry 4.0 is a term that was introduced in Hannover Messe in 2011. And it's about a new stage in the development of production systems. So the main difference of the fourth industrial revolution in comparison to the previous ones is that it presupposes mass production of highly customized products through the use of so-called cyber physical systems. So the customers now want really they don't want just gray boots or some, I don't know, some really general products. They want these products to be personally oriented to themselves, and this um, it makes it necessary for the manufacturers to change also. They need to change fast. They need to reschedule fast. They need to have really transparent assets on their plant, etc. They need to have so-called cyber physical systems. Cyber physical systems are the systems that are closely integrate physical and IT components. So all hardware should become smart, not only because it's smart on itself, but also because it's smart because since it's connected to the IoT infrastructure. And now I'd like to show how Siemens see this digital transformation mainly for manufacturing. Siemens has a vision that this digital transformation means moving towards fully integrated value chain of a product. So we have here a concept of digital twin, and we have three digital twins here. It's first of all digital twin of a product, it's digital twin of production, and digital twin of performance. So let's see step by step how these digital twins work. First of all, in the first step, we need to understand which product we want to produce. And this can, in paradigm of digital enterprise, it can be performed in the fully virtual environment. So we have special products that enables to model all the physical and not only physical characteristics of the product to build this a model of the physical product, and then it is performed in so-called digital twin of a product. And then at the second stage, we need to understand what production we should have in order to produce the product that we have designed. And this also can be performed in the fully virtual environment in so-called digital twin of production. This enables to significantly reduce risks in comparison to building physical production without modeling. And then on the third stage, we have real production where we have automation, and this production produces real product. And then we collect really lots of data from production and from the product after these products are used. And this data is collected in the so-called digital twin of performance. And then based on this data, we gather first of all this data, and then we continuously improve both the product itself and its characteristics, and the production and its effectiveness, etc. So we have so-called closed loop here, and we can constantly improve our product and production based on actual data that we get from the real production and the real product. And what is the role of IoT platform here? Is it's quite clear. Just get back to the previous slide, and that's to collect all the data to digital twin of performance. We need to have a kind of storage. It can be located in the cloud, and we need to have some sensors that collect data from this production and the product. And then based on this data, with the use of industrial IoT technology, and we can optimize the whole process. So the IoT platform enables to make this thing faster, cheaper, and with more with less risks. I will explain why. First of all, I would like to show MindSphere IoT platform is a Siemens platform, just to understand how IoT platform how it's what consists of. So we have generally 3 layers. The first layer is connectivity layer. Its layer enables to fast connect of products, of plants, of other sources of data, and via secure and safe transfer to collect it in the second layer, which is the MindSphere platform itself. And then on the third layer, we have special applications. We have lots of applications that are developed by customer, by our partners, by Siemens internal labs, and these application and instruments that we have on our platform allow us to solve different problems, to analyze data, to visualize it, and to make a decision based on actual and objective data. So again, we have 3 layers. First of all, we need to collect data from necessary data sources. For this, we have connectivity layer. Then we need to store this data. For that, we have MindSphere platform that is located on public cloud, for example, Amazon Web Services or Microsoft Azure. It's public cloud providers that MindSphere is located on. And then thirdly, we have application layers that enables us to extract value from data we have collected. And since MindSphere is a ready-to-use solution, it has a lot of out-of-the-box components, which allows to create a new solution really faster and cheaper and with less risks. For example, if we make a solution from scratch, we need to provide connectivity. We need to manage some IoT gateways, to provide networking, to manage storage. We will have hot, warm, cold storage, etc. We need to build applications based on that infrastructure, and this really has lots of capital expenses, operational expenses, and lots of risk. If we have out-of-the-box solution, we can just connect necessary assets via standard protocols, because we already have prepared this package to connect necessary assets. Then we have ready-to-use industrial connectivity. We have also prepared storage, and also lots of applications ready to use, and lots of instruments that allows us to build these applications faster by ourselves. So in the second scenario, we have approximately 60% less time needed to create such solutions, less expenses, and significantly less risks. Then we have so-called Forrester Wave report, which places the strongest players on the IoT platform market, and we see that the currently top players are Siemens with MindSphere solution, and also competitor PTC with its ThingWorks platform. It's just to understanding of the market landscape. And then if we're talking about extracting value from data, it's also clear how to move here. First of all, we should provide monitoring of the assets. So we need to provide the general transparency so that to understand what is going on the enterprise. Then we, in the second stage, we provide analytics. So we use some algorithms or root cause analysis tools to understand the general causes of some issues that are happening on the enterprise, and that enables us to make our enterprise more effective. And then we have the third stage of maturity of such IoT systems, which is predictions and optimization. So we want to, and we can embed some machine learning or other artificial intelligence algorithms in our solution so that it can predict the quality of the final products, or it can predict some failures which are happening with the equipment, and we can even provide some automatic recommendations to the operators of the machines, and it of course enables to improve the efficiency of the production significantly. And now I would like to show one example for each stage so that you have some concrete view of that. So let's start with the monitoring. I will show the use case with the overall transparency on the plant, and with monitoring of so-called OEE factor. First of all, on the enterprise and on the manufacturing plant, we have four main sources of loss. So ideally, we have ideal assets that are working 24 hours, 7 days per week. And the real assets have, first of all, planned downtimes. For example, if we have the planned service or something like that. Secondly, they have unplanned downtimes if we have some failures with the assets, or if we have some problems, errors with that, and this time the assets don't work as they have to. Thirdly, we have performance losses. It's connected with little stops with reduced speed, so that the machines don't work on their full energy, let's say like that. And then final loss is connected with quality. It's connected with some scraps, some rejects, rework, etc. And OEE factor, overall equipment effectiveness, allows us to have these all factors in place, and it's calculated like quality factor multiplied by performance factor multiplied by availability factor. And it can be as a general factor that allows us to compare different machines that can produce different products and with the same criteria, this factor OEE. And for this thing, to visualize this factor and to allow us to enable more transparency to the plans, we at Siemens have a special solution which is called OEE Monitor. And I will briefly show it in a short live demo. So it is a web interface of MindSphere platform. Colleagues, can you say, please, do you hear me? Because I'm not sure.
Yes, we hear you.
Okay, thank you. So we have this MindSphere Launchpad, so-called, and we have different apps that we can go to. And one of these apps is OEE Monitor, which allows to, first of all, monitor this OEE factor and its components, which are availability, productivity, and quality. We can monitor these parameters at the machine level, so we can go to the single machines, or we can monitor these parameters on the line level. So if we have several machines that are working in line, or we can monitor it for the whole plant. We have several lines, for example. In this scenario, we have two lines that are producing HDD disks for computers, and we have three machines for each line. So, for example, we can go to this, for example, packaging machine. We can see which OEE was, for example, for the last 7 days, 30 days, etc. We can see all errors that was happening with the machines. We can see in which this machine loss in effectiveness. So using this not really difficult application, not really with deep analytics, we can understand the reasons of OE losses and all, for example, quality losses, productivity losses, and availability losses, and to understand which measures we should have in order to increase it. And after that, we can evaluate trends. So if we, for example, have some measures prepared, we need to understand that OEE is increasing for real, that it's not only in papers or just we are talking about its improvement. We have objective criteria that allows us to see that the OEE is increasing. So it's about the first solution, which is about monitoring stage. And then we go to analytic stage, which provides more complex analytics tools. And for this, I would like to show you another use case. It's a use case that Siemens provided for Nestle. You know all Nestle company. It's really a huge international company, and in this use case, we have one of their plants, which is called Yuka plant. It's located in Finland. It has 4 million kilograms annual production, more than 100 recipes for premium sauces, and really various raw material suppliers. And Yuka and Nestle wanted to increase plant output and operational efficiencies, and they wanted to build strategy for the next 5 years. And I would like to show the solution that was suggested and that was implemented then here. We have here really bundle of products. First of all, it's a simulation product that allows to virtually simulate all the production facilities on the plant and to build so-called digital twin of production I mentioned before. And let's see how it looks like. So the full virtual copy of the production was built, and we can see it in 3D view, in 2D view, and to see actual data, to analyze different scenarios, to um, to see what happens if we changes one parameter, how it affects the output, etc. So we can provide all we want in a fully virtual environment here. And it's all performed in a single environment, which is called Technomatics Plant Simulation. It's a Siemens product. And then we don't only suggest this product, but also integrated it into another product, which is called Projector Scheduler. It's the tool that enables to schedule and to plan the workflows, etc. Also in the fully virtual environments. You can see now how it looks like. So instead of just planning in Excel, it significantly reduces efforts because of automatic rescheduling or etc. And integration with Technomatics Plant Simulator, which I showed before, enables to really makes planning more efficiently, because before planning, we can simulate all the results of this planning in fully virtual environment. And if this planning is not efficient enough, we can make a different one, and then physically we provide really efficient planning. I will not go in many details. I will go to the industrial IoT solutions now. This solution was built based on MindSphere platform, and it was also integrated with the previous two products, and it enables the digital twin of performance I've mentioned before. So we collect data from, in this case, from cooking machines, and a special application was developed specially for this customer, and I will show it a little bit later. But first of all, we have a standard application which is called Fleet Manager, which enables to view raw data. For example, in this scenario, we have kettle statuses and orders that we get to MindSphere. They are collected, and we can see them. We can see their raw values here. But analyzing raw values is not really easy. It's not really good. And so we have a specialized application that was developed especially for this customer. And I will show its interface now. So it's a custom application which allows to see all assets intensities and losses week to week. So we can see the reports here automatically calculated based on the actual data. We can drill down to individual assets. In this case, it's kettles. We can see all necessary information. We can overview the whole process of cooking. We have here 8 kettles here, and we can visually analyze and to detect anomalies which are happening with these kettles. And we really can notice that something happens and some anomalies take place in that case. And then, for example, in this case, we have another tool which allows to have a root cause analysis. And this tool, after we noticed on the app I've showed previously that we see some problem, we then go to this root cause analysis tool, and we can see which particularly and in concrete case, so what brings to these problems, what root causes it has. So in this case, we have one kettle, for example. I will show it here. Sorry. Yeah, we have that one kettle really differs from another in point of output. We have one kettle that is a bottleneck of this problem. So with this tool, we can really localize the problem and to understand the source of the issue. And we then can go to this kettle and to repair it. Here we have kettle 6. It's almost 30 minutes longer than other kettles to heat. The process and to solve the problem. So it's the second scenario I would wanted to show you. And then the third case with the predictions and optimization. Here I want to show you the solution, just an example, which is called Smart Machine Assistant. It's a special artificial intelligence application that is needed to optimize complex machine operations. So the problem is that there are lots of complex machines that are really that are really affected by the external factors. For example, if we have temperature changes or we have moisture level changes, it can start to produce less worse products, or it can provide worse output, etc. So if the machine is sensible to the external environment, it's really a good idea to optimize its settings based on external parameters. So the use case is the following. We collect data. First of all, it's settings of the machine, and secondly, it's the external parameters. For example, temperature, moisture level, for example, a type of raw material, etc. And then we build a machine learning model based on this data, and this model understands that the particular parameters provides the best result. And then, if we have changed the external factors, this machine learning model can say to us that you operator have to set these settings for the machine so that it it provides optimal output. So we have this self-learning AI algorithm, and this machine learning that helps us allow unknown dependencies in the operation, etc., etc. And as a result, we have, for example, in this particular use case, it was provided for Volkswagen. It's a press shop, and as a result, there was a significant reduction of non-conformance costs. It's 2 or 3%. It's in added value. It's really high. And we also had improved quality and improved machine performance. So added value was about 600,000 euros per year for a single press line. And I can just now show you the live demo of this smart machine assistant interface. It's really a simple web interface that allows the operator to see what he has to do. For example, if we have a hydraulic press, and this hydraulic press has 8 cylinders. This application can show that the pressure in some cylinders is good. So the recommended value is approximately the same as the current value, but in some cylinders, current value is not equal to recommended value. So that operators see that in order to have better result, he has to increase, for example, in this case, pressure in the second cylinder, and also decrease the pressure in the fifth cylinder, and to increase the pressures in 6th and 7th cylinders. And this action brings us to the better output. So in this case, this solution allows us not to be dependent on some knowledge and some expertise of the operator. It enables us to just show him what to do, and it significantly reduces requirements for the level of operator's knowledge. And also it increases the effectiveness of this machine. And effectiveness can be measured in different criterions. For example, it can be effective in the quality perspective, it can be effective in the output perspective, or it can be effective in the stability perspective. For example, if we're talking about gold mining industry, it's really important to have stable process. But if we are talking about, for example, cement industry, it's really important to have the best quality, because the main competition is for the quality in this industry. So we can optimize the parameter, the machine settings in the perspective we need.